This is John working with my students. Unfortunately, the first student cannot get his visa after 2 months of waiting, so I present the papers for him, but credit should go to the students. This work is about how we design a scheduling framework for distributed LSM-tree-based storage. We have a lot of unstructured data, and the common way to manage this unstructured data is to use key value stores, which provide a high-performance, flexible data model for managing the unstructured data. And right now, key value stores are also used for AI and machine learning systems. To support a large amount of key value store data, so we use Cassandra as a starting point to understand about how it works. So we have to distribute the data across multiple nodes. So there will be 2 layers here. The first one is the distribution layer, which uses consistent hashing to map the data to different key ranges, where each key range will be managed by a node. And we also use replication to make copies for the data to achieve fault tolerance, but not just fault tolerance, but also load balancing, so that we can distribute the read or write loads across different nodes. And in the storage layer, each node actually uses an index structure to manage data. And in Cassandra, it uses the log structure merge tree because it achieves high performance writes, efficient reads, and also scalable storage. However, we have a lot of load balancing strategies for distributed key value stores, but we see that latency fluctuations are still very common. And this will introduce high tail latency, where the high percentile latency is much bigger than the median latency. And so we argue that there are 2 main root causes. The first one is the load balancing strategies used in the distribution layer is not very efficient. And even though we distribute the request evenly across all the nodes, latency spikes could still occur. And if we look into this in more detail, it's because there is task interference in the storage layers. So in the storage layers, it needs to serve the foreground reads, which involves a lot of random reads. And at the same time, the LSM tree needs to perform background compaction. And this will introduce significant CPU and disk IOs. And also, this compaction is asynchronous across nodes, so it's very difficult to coordinate all the nodes to balance the workload. So here comes our contributions. We designed a system called HAS, a holistic and automated task scheduling framework for distributed LSM tree key value stores. And the main idea is to co-schedule the read and compaction tasks. So HAS introduced 3 techniques: coarse-grained read task assignment, fine-grained read task coordination, and also compaction task scheduling. And we compare HAS with state-of-the-art distributed key value distributed LSM tree stores, and we show that we can reduce the 99 percentile latencies by 58.6% and 59.9% respectively. So let's start with a toy example to see why load balancing is so challenging and how we should address them. First of all, we noticed that actually if we just simply balance the access frequencies, it doesn't imply read latency balance. So here we consider a small scale cluster with only 10 nodes using 3-way replications, and all the nodes are homogeneous, have homogeneous hardware. And we find that actually there will be fluctuations in terms of the latencies. Now, even though we apply replication and we deploy the default load balancing techniques in Cassandra, which is called dynamic snitching, it can reduce the variations between the latency. It can reduce the load, the distribution of loads. If you see the max load divided by the min load, we can reduce this using replication. However, if we look into the latency, if we divide latency, maximum latency by the minimum latency, actually it could go to 4.24 times, which means that the latency actually fluctuates a lot, even with a very simple, even with a toy sample, even if we deploy the load balancing strategy. And also, if we look into a smaller time scales, actually, we see that there will be high fluctuations. Now, in large scale, like 1 minute window, actually is quite smooth. The latency distribution is quite smooth. But if we look into a smaller time window, 1 second window, actually we will see the latency fluctuations. And the reasons behind is because they're like dynamic foreground IOs and also transient background tasks, which they couple together, and this will introduce latency fluctuations. And also the asynchronous nature of these activities will also create a load-level imbalance. Now, if we look into the coupling of the read task and also compaction task, so here we run the experiment. We focus on one single node, and we execute the workload for 30 minutes. We disable compaction the first 10 minutes, and then enable compaction, and then disable this again. We find that as compaction is enabled, the read throughput will drop from 26.3 kbps to 7.3 kbps. Now, so one thing we can argue is, hey, can we just rate limit compaction? However, it's not good, because if we see that after compaction is disabled, we see that actually the read performance will improve. So actually compaction by itself is not bad, because it helps to remove the stale key value pairs and also make the key value pairs sorted in a compact way, and we can actually improve the read performance. So, so we should not just simply rate limit compaction, but we should coordinate the compaction task with read tasks carefully, and this is the main motivation of our work. So here's an overview of HAS. Okay, so it contains 3 components here. So first thing is we apply coarse-grained read task assignment to try to address the predictable imbalance over large time scales in epochs. So in Cassandra, it will have an epoch set in 60 seconds. So we try to do the load balancing at the large time scales. And then later on within each time scale, we try to react to some unpredictable system conditions through the read task coordination in a fine-grained manner. And also, in the node level, we will schedule the compaction task based on the read loads. So put together, we will try to achieve holistic automated task scheduling to achieve load balance. So let's start with the first component, coarse-grained read task assignment. So we need to address several challenges. First of all, we just showed that balancing access frequency is not sufficient. So we need to not just look into the access frequency, but also the latency. So we need to collect these read loads from other nodes. And also, when we schedule the task for one key range, it can also interfere with others because each node actually serves multiple key ranges. So when we do the load balancing, we need to have a global view to compute the balanced read loads. Now, given these considerations, we also need to address the third challenge is we need to collect the cluster-wide read loads to do this load balancing, but this collection can introduce significant overhead. So our idea is to augment Cassandra's gossip protocol to share the load information. So here what we do is Cassandra itself actually uses the gossip protocol to share the membership information. And we extend this gossip protocol to include the latency information. And at the same time, when we do the load balancing, we need to select some nodes to be responsible for the scheduling. And we select a few nodes for this scheduling. And we use the raft protocol to ensure that if one scheduling node goes down, we can still have another scheduling node to help out do the scheduling so that we can achieve reliable scheduling. And for reasonable size of a cluster, typically we find that in practice it will be just about a few hundreds of nodes. So if we use 100 nodes and three-way replications, the communication overhead is only 15.2%, which we argue that is acceptable. So So then, based on the collection of the read loads, then we run the algorithm to adjust the read load. So the basic idea is we try to share the read requests across the replicas. So each replica will receive a proportion of the read requests, and we try to move the read loads from high load replica nodes to low load replica nodes, so that each node will, based on the current load, it will receive the corresponding portion of read requests. And the algorithm actually is quite efficient. It's linear complexity, linear to the number of nodes in the cluster. And also the execution is infrequent, it's only performed once per epoch. So we argue that the algorithm overhead is small. And then on top of that, remember that each replica will receive a portion of read requests, and then we will each node will also look into the current load and try to reroute the read request to other replicas if necessary. So the idea here is we compute a score for each node. So this score basically tells us about the extra capacity of how much more read requests could be handled. So intuitively, high score means that each request can serve more extra requests. So the idea is if one node finds that there are other replicas with high score, then we will just reroute the read request to the other replica nodes. And by the way, this is quite similar to the current dynamic snitching module in Cassandra. We just augment this dynamic snitching module with the score calculation. Finally, we will do the compaction task scheduling. And so there are two main elements here. The first one is we do the replica decoupling. So the idea is each node will store the replicas for different key ranges, and we will do the decoupling so that each replica will be assigned with one LSM tree. This idea was proposed in earlier work. And then based on that, we will just assign the compaction rate proportional to the read load, because our argument is the compaction is helpful to the read performance. So for the replica that receives high read loads, it will also receive high compaction rates. So we will do the experiments on a local cluster. We compare with different baselines. All these baselines are built on top of Cassandra version 5.0. And we use the YCSB synthetic workloads and also modeled Facebook production workloads. So first of all, we want to ask whether coarse-grained and fine-grained schedulings are really necessary. So we look at the coarse-grained scheduling. The coarse schedule, actually, it can increase the throughput over the baseline, but only slightly reduce the tail latency, because it doesn't react to the current conditions, system conditions. So we also need fine-grained scheduling, and then we see that actually it could reduce the tail latency further over coarse-grained schedule. And hence, basically, on top of fine-grained scheduling, it also applies to compaction task scheduling. So it can mitigate the compaction interference. So if we look into the error bars here, so these error bars are the confidence intervals. And we see that if we apply hash here, we can reduce the error bar. So essentially, that means that we can reduce the fluctuation caused by compaction. So that's how hash achieve low balancing and also reduce the tail latency. We also run the systems on YCSB benchmarks, and again, has also achieved high throughput and also lower latency. And also for modeled Facebook workload, we see also similar trends as well, where hash actually maintains the best performance. So here comes our conclusions. Hash is a holistic and automated task scheduling framework. Although it is built on Cassandra, but in our paper, we also argue that it could be applicable to other distributed LSM-tree-based key value stores. And the goal is to improve the system throughput and, most importantly, mitigate the latency fluctuations. And Hash is open sourced, and so please feel free to verify our code. Thank you. I'm happy to take your questions and comments.